All right, I'm going to go to example 3. Example 3, continuing forward, we are going to solve an initial value problem this time. And since this is not the classroom environment, we may actually have time to solve this out. Again, I start this out using the same tactics that I used before. So let's pretend that there's no similarity between this problem and the previous problem. It's actually very close, right? The only difference is the minus sign here versus the plus sign in this problem. However, let's just pretend as though this is an exam or something like that. And sorry, I'm going to adjust my mic here. And we're being asked to jump right into this without having solved something similar. We're always going to assume for Cauchy-Euler that the solutions are of the form y equals x to the m, which will imply that y prime again is m x to the m minus 1, and y double prime is m times m minus 1. Now, obviously, you do not have to continually write this because at some point you just get it, how it goes. It almost looks like a factorial as the coefficient. And so you get really used to it and you zoom through it rather than having to memorize this. In the end, you know also after having done a few of these problems that it's going to be x to the m times the quantity. Let's see, y double prime will have the m times m minus 1. The x to the m minus 2 has been factored out and multiplied by x squared. Minus 3 times y prime, which is m. The x to the m minus 1 has been multiplied. I'll show you here. The x to the m minus 1, this guy right here, has been multiplied by the x to become an x to the m and has therefore been moved out front. And finally, you have plus 4 times y. And again, y is just x to the m, which has been moved out front, is equal to 0. You can pause this and work through it if you want to. The only piece that will contribute to this product becoming 0 is the m squared minus, oh, look at this, minus 4m. I didn't recognize there was complete difference in signs there, so that's actually minus 4 of those m's plus 4 is equal to 0, right? A minus m from this first term and then a minus 3m from the second. And of course, this is factorable, m minus 2 quantity squared. We have repeated roots. And we know from our theory that if you have repeated roots, you'll attach a natural log of x in front of your solution. So in other words, you will have a full solution y sub c, which is equal to some constant, x to the 2 power, because that's what the root is for this equation. And because it's repeated, the second solution via what we did, which was reduction of order, is going to be the natural log of x times x to the second power. So again, repeated roots, you just attach natural logs for Cauchy-Euler equations. And now what we're going to do is go ahead and solve the IVP for the first time in a long time because we have time here. So I'm going to let the output be 5 and the inputs be 1. However, if you let the input be 1 for this, you'll see that the natural log of 1 is 0, so you get that C1 is equal to 5. Now you'll also need to know what y prime is, so I'll go ahead and y sub c prime. That's just going to be 2 C1, which is 5x, plus, and then taking the derivative here, you see it's going to be a product rule, so you have c2 over x times x squared plus c2 twice c2 natural log of x times x. Oops, just x. I'm not really going to simplify this because we happen to know that we're going to be plugging in 1 for x. The output should be 3. So I'll say the output is 3 when the input is 1. So we have 10. Remember this is going to be plus c2. The x's cancel if you want to call it that. And then natural log of 1 on the back end is just 0. So I'll write it that way. So c2 should be a negative 7. There we go. Our final full answer is y is equal to. Notice that I dropped the subscript of sub c. It's a pretty good habit to get into when you get particular solutions, like not a general parameter, a family of parameters solution, but an actual solution to this. So it is going to be 5x squared minus 7 natural log of x squared. That is the solution to the original Cauchy-Euler differential equation. All right, that's it for this one.